Okay, so this mini lecture is going to introduce you to a variety of thermodynamic processes and the equations that are used to analyze those thermodynamic processes rooted in the first law of thermodynamics. And so we'll do a derivation of a couple of them, and then we will look at really the relationship for other ones. And then in some other mini videos are some example problems. So look for those. Okay, we're going to talk about a few different thermodynamic processes and a little bit about what assumptions we're making about them, and then, like I said, how the first law applies to them. The first one that we're going to talk about is what is called an isothermic process. Iso meaning the same, thermic meaning temperature. So what this is telling us is that there is no change in temperature during this process. So another way to think about that the temperature is constant. Okay, so if we're holding the temperature of a situation and the temperature is going to remain constant. Okay, let's look at that impact and what we know. If we look again at the ideal gas law, and we're going to use that as sort of our assumption, which isn't a bad assumption. And we know that in the ideal gas law, PV equals nRT. Well, if temperature is constant for a given amount of gas, and R is a constant, N is a constant because it's the number of molecules, then PV also has to be a constant, okay? If PV is a constant, then when one goes up, the other has to go down, all right? So just kind of keep that in the back of your mind. Now, what happens in an isothermic process when we add heat? Okay, so we're going to add heat. And this is really where realizing that heat is energy versus temperature is going to be important, because if I'm adding heat, I'm keeping the temperature the same. So what does that give us? Okay, that's what's going to be important as we think about these things. So if I add heat and we think about the first law of thermodynamics, we know that our change in internal energy is equal to our heat plus the work. Okay, our heat plus the work. But we know that the internal energy is based on temperature of an ideal gas, right? The internal energy is based on the temperature. So if there's no change in temperature, this implies that the internal energy does not change. So in an isothermic, that's not what I want to say, this should say thermic. There we go. In an isothermic situation, our change in internal energy is going to equal 0. Okay, so what does that give us? Well, that tells us that the heat is equal to the work, and is it done by or done on? Done by the system. Sorry, on, by, oh gosh, negative. So this is the work done by the system. So the heat can do work. What does this work do? What can adding that heat do? Well, that's going to come back to Pivner. So if I do work on the system, I can change the volume of the system. So let's imagine that we have like a piston in a container. So here's my piston. It's free to move up and down. If I add heat to this system, I can do work on the piston. My volume can increase, so I can do work by pushing that piston up. Okay? All right. So the key here, written another way, is that for isothermic, the heat in is equal to the work out. So how much heat I put into the system is how much work I can get out of the system. All right, so that is isothermic. Okay, the next one we're going to talk about is an adiabatic process. Now, an adiabatic process is something different. This is when no heat is allowed to enter the system. You might think, well, under what conditions can that happen? Where no heat enters. And a diesel engine is a really good example of that. So erase this, we already used that. Okay. This is no heat. No heat is allowed to flow from the system into or out of the system. Okay, so how does this happen? Well, if we have a rapid expansion of gas, for example, in a combustion engine, this is an adiabatic process. So what implications does it have if no heat is added in? Let's go back to our first law of thermodynamics, where my change in internal energy is equal to heat plus the work done. So if no heat is added, then my change in internal energy, what am I writing? My change in internal energy is equal to the work. So pretty straightforward. If the work is done by the system, this is positive, and the temperature goes down. Back that up. If the work is done by the system, this is negative, whoops. These are our implications. If the work is done by the system, the change in energy is negative. The work is negative. The change in energy is negative. That means the temperature went down. If the work is done on the system, the work is positive, based on our definitions before. The change in energy is positive, and that means our temperature went up. Okay. So, for example, a diesel engine. Okay, I said that idea of a really fast combustion engine. So if we take that mixture, that air mixture of fuel and air, okay, and we rapidly compress it. So we do work on the system by rapidly compressing it faster than we can get changes in heat, or heat can flow, then the temperature of the engine goes up, and it goes up so fast that it causes ignition. You don't even need a spark plug. So a diesel engine works that way. We get a really rapid change in rapid work done on the system. Temperature rises very quickly. We get ignition without a spark. So there's our example of an adiabatic process. No change in energy. Okay. There are two more processes that I just want to mention, and then our little review will be done, and you can look for some example problems. So the next is an isobaric process. An isobaric process tells us that there is no change in pressure. So no change in pressure. And an isovolumetric process, volume, no change in volume. So a couple more pieces of language there, and we're going to look at work more in detail in some of these processes in a couple other mini lectures, so check those out. So just an introduction to some of the terminology, some of the assumptions or implications that happen with that terminology in dealing with processes related to our thermodynamic processes. All right, good job.